Okay, I now want to turn to interpretation of the mixed model, and we've kind of already looked at this in the Oxford data example, but I'll do it in the general setting. So linear mixed models can be used as a target of inference in one of two ways. First is what we call the population interpretation. And under this interpretation, the LLM is interpreted by a marginalization, that is to say, by marginalizing over the random effects, so that the way we interpret it from a population level is that yi given xi is normally distributed with mean xi beta and covariance structure given by that expression there. So in the population interpretation, interest is only really an estimation of beta and in decomposition of the error variance via estimation of the variance components. That's what we're interested in. We're not interested in the random effects necessarily per se. Second, we can have a subject-specific interpretation of the linear mixed model. And here the random effects are important because the linear mixed model is interpreted for each subject I conditional on the random effects. Yi given Bi is normally distributed. This time the mean is Xi beta plus Zi Bi, and the covariance matrix now is just lambda I. So notice the difference here in the two means. In the subject-specific interpretation, the mean is no longer just Xi beta. It's Xi beta plus the random effect part. And we're adding that random effect component because we're conditioning on it, as you can see here. Interest then in the subject-specific model is in estimation of beta and in what we call prediction of the value of Bi for each subject. We don't call it prediction. We don't call it estimation of Bi. We call it prediction. We'll explain that later. And as we'll explain, the random effects can be predicted using this formula shown here. And intuitively, this should make sense. So y minus x beta hat isolates the composite error in the model, and pre-multiplication by psi z transpose sigma inverse extracts the random effects from that composite. So that's the way it works. With the predicted random effects in hand, we can then quantify the subject-specific fixed values in this expression here. Now we'll consider each interpretation in turn and then explain the estimation procedure required to realize them. So the population interpretation. The population interpretation matters because linear mixed models can accommodate complex error structures, and that allows considerable flexibility in modelling the marginal covariance of the response variable y. The covariance matrix psi may be unstructured or structured. For example, it could be diagonal, and it's parameterized by a set of parameters called theta. The lambda I matrices are typically assumed to depend on I only through their dimensions, parameterized by a fixed small set of parameters that we call lambda. So this flexibility in the population interpretation gives two ways to accommodate non-spherical errors. First, via the random effects themselves. Since the BIs are subject-specific and do not vary with time, so within subjects' observations share the same random effects and are therefore by construction correlated. Correlation is just generated in that simple way through the random effects. And this is represented by the Zi psi Zi transpose part of sigma I. Note also that the diagonal elements of that matrix need not be constant, so it can accommodate heteroscedasticity as well. Second point about the population interpretation of the linear mixed model is that within subject errors, their contribution to the marginal covariance is lambda I, which can be non-diagonal, that is correlated, and of different diagonal elements, can be heteroscedastic. So both components, these two components, give us a lot of flexibility, all specified parsimoniously through a small set of parameters. Now we'll turn to the subject-specific interpretation of the linear mixed model. That interpretation allows the model parameters to vary by subject and the random effects are the intuitive quantities representing between subject differences in coefficients. So as in the Oxford model we showed earlier, where each boy is able to have their own intercept and their own deviation from the average slope. The random effects are represented in the model via the variance components in a parsimonious fashion. So the 52 random effects in the Oxford model for intercept and slope, 26 pairs, are specified by just 3 additional parameters. The 2 random effect variances, sigma squared beta naught and sigma squared beta 1, and their covariance. To calculate the random effects, we first need to estimate the unobserved parameters that determine them. Psi is a function of theta, and lambda is a function of lambda, or big lambda is a function of small lambda. And one point of terminology, in linear mixed model language, we predict random effects while estimating fixed effects. I mentioned that earlier. The difference is that the target is random for the random effects, but deterministic non-random for the fixed effects. And that's why we write a tilde over the predicted B's rather than a, let's see if I can find an example of it. It should be somewhere here. Yeah, we write a tilde over the predicted B's rather than a hat as we do, because this is hat denoting estimation, and this is the tilde denoting prediction.